friends, hope that you are in fine state of mind and health there with another video regarding the important properties related to the wave function. I'm back here again. As you know that what is the importance of wave function in describing the quantum mechanics, already we have come across, and in this video we'll try to recap some of our earlier ideas and also discuss some new things like equation of continuity and some kind of things that lead to in understanding good behavior of a wave functions. So these are the two parts of the video that we'll discuss: equation of continuity, normalization conditions, and then different kind of conditions related to good behavior of a wave functions. And we'll see that equation of continuity will lead to how the good behavior of a wave function is determined. And one thing that we must remember that already we have discussed about normalization conditions and conditions for well-behaved wave function in the earlier videos, but still we'll take a short recap on them, since equation of continuity must be discussed while discussing these different conditions of well-behaved wave functions. So let's start with the equation of continuity in this video. So rewriting the time-dependent Schrödinger equation in this way, that is equation 1, this already we have come across, and also taking that potential is independent of time, and the conjugate equation for equation 1 is this one. We conjugate means that this complex conjugate will be taken over the complex things, since psi is a complex quantity, so we take psi star, and everywhere psi star is there, and b is a real kind of thing, so there is no star mark is there, and this I will become minus I, and equation 2 is nothing but the complex conjugate of equation 1. Now we multiply equation 1 by psi star, that is complex conjugate of psi, and from the left hand side, and then equation 2 by psi from the right hand side, and subtracting the results, that means subtracting the second from the first one, we get this. So we multiply this equation by psi star on the left hand side as well as on the right hand side from the left side, and multiply this equation 2 by psi from this right hand side, and subtracting the second result from the first one, we get an equation like this: I cross del side of psi star equal to minus a cos square by twice m psi star nebula square psi minus psi del psi nebula square psi star, equation 3. Then the right hand side of equation 3 can be written, this right hand side of equation 3 can be written like this equation, this nebula dot psi star psi nebula psi minus psi nebula psi star, equation 4. So equation 3 now takes the form this one. Equation 3 with the help of equation 4 takes this form. So interchanging the minus sign here, these two terms, so we have minus I cross by twice m nebula dot psi nebula psi star minus psi star. So this is simply minus sign is put here, and we get equation number 5. And in equation 5 we define this psi star as rho and this quantity by j, so we are left with del rho by del t minus divergence of j. So this is this, if we put I cross by twice m here, this part I cross by twice m into this equation within the bracket will give us j, and equation 5 will now become this one with interchange of left hand side and right hand side, bringing the right hand side on the left hand side, and we get an equation. This equation 6 is known as equation of continuity, and this equation is quite familiar for us. It is found everywhere in electrostatics, in fluid dynamics, or in case of electromagnetic theory while discussing Maxwell's equation. And this rho is nothing, it's a psi star side, that is modulus psi square, so it's a probability density, and this j, the new quantity as defined here, is the probability current density. And this j can also be written like this: this RE of within this bracket I cross IM psi star nebula psi, this is equation 7, whereas RE stands for real part of the expression within this bracket, and the 2 here will be will be cancelled off, or because we're taking real part of this quantity, and this minus sign is included here with a real part of, with a consideration real part of the quantity here. So if we break up these things, then it will give us again this quantity. So 7 is the definition of current density, probability current density in quantum mechanics, and always it's a real quantity because RE term is, because, and that's why we are putting RE here. And for one dimension, we will take the x, for say x dimension, it's only that this nebula score, this nebula will be replaced by del by del x, and it's like this. For jy it will be RE a scores by IM psi star del psi del y. For jz it will be RE a scores by IM del psi star del psi del z. So only things that for dimensions will replace x by y or y by z like that way. And for one dimension case, this nebula will go, it will be replaced by x, y or z, whatever we think of. Then we recap the normalization condition again here, and this was the normalization conditions. And as we know that normalization condition is simply is the statement that the probability is conserved, or for maximum probability is 1, and this is actually representing that maximum probability is 1. And in the case that sometimes this is not equal to 1, we multiply this by a constant and 1 by n square, and in that sense it becomes this. And this new wave function is now psi 1, and this psi 1 is the normalized wave function given by psi by n. So this already we have discussed, and normalization simply means the probability is conserved and probability is maximum probability is 1. And these two conditions, if already this normalization condition is automatically 1, then we need not to bring a constant, and if it is not equal to 1, we need to bring a normalization constant. Again, we recap that what are the conditions for well-behaved wave functions. These are the conditions that u must be finite for all values of r. We are taking the time independent wave function. Remember that this good behavioral wave function is valid for psi also. Psi means the time dependent part of the wave function, or sorry, time dependent wave function. So we are only considering here in time independent wave functions. So ur must be finite for all values of r, ur must be continuous for all values of r, nebula ur must be finite for all values of r, nebula ur must be continuous for all values of r. And the last one, that ur tends to 0, that means the wave function would become 0 if the dimensions becomes plus minus infinity, or this xyz goes to plus minus infinity. So it's another, this is a simply a statement that the wave function is always finite, and even if the dimension goes to infinity, the wave function always gives its finite behavior. So these are the 5 conditions that determines the well behavior of a wave function. Okay. Now, how these conditions follow, let us discuss these things. The condition 1 follows from the fact that probability is finite, because if you see u, what is u? U is nothing, it's related to probability. Since probability is finite, so this u must be also finite, because modulus of u square gives us the probability. Okay, so this condition 1 is valid because probability is finite. Then condition 3 is followed because j is also finite. J means probability current density. If you look at the expression for probability current density here, it composed of psi star and these things. Since psi star, all these things are finite, so definitely j is also finite. Remember that although we are using u here, that already I said that it is also valid for psi also. So this j, since j is finite, so that means that j is finite, that condition 3 follows from that fact. Now, since condition 3 is correct, it means that j is finite. If j is finite, that means that this must be finite, because j is given by this. If you look at here, this j is given by this. Since psi is finite, so definitely this psi is finite, and also nebula psi star is also finite, or nebula psi is also finite. Or if you look at here, equation 7, this nebula psi is finite, that means since j is finite, nebula psi is finite. So since nebula psi is finite, from the concept of differentiation, we can say that this u must be continuous or psi must be continuous. And again, this nebulized core u is finite for all value of r if Vr is finite. Okay, Vr is finite because it is finite because it is related with kinetic energy or in the expression for Schrödinger equation. So since this is finite, nebulized core u is finite, so this must be continuous. Always we must remember that if the nebula u is finite, u is continuous. If nebulized core u is finite, then nebula u must be continuous. So this is one of the boundary conditions also known in quantum, well known in quantum mechanics. Because if Vr is a finite quantity, then this will be finite because of Schrödinger equation. And since this is finite, this must be finite. And this is nothing but your condition number 4 here. This is continuous. So for this must be continuous, nebulized core u must be finite. And nebulized core u is finite because V is finite. It is followed from Schrödinger equation. Now, if Vr is infinite, then this is not continuous because this nebula u is not continuous because nebulized core will not be finite in that case from the Schrödinger equation. And in that case, we take the wave function will be vanishing at the points where the potential is infinity. And this will be well known in case of our well discussing infinite potential well in the coming course of time, that where the potential is infinite, that the wave function vanishes there. This is one of the boundary conditions that we must take account of. So all these conditions 1 to 5, all these conditions now followed from or the own definition of all these things, from probability definition, from current density definition, as well as following from one condition to another, just like this. If this is finite, then this is continuous, which is condition number 3, and this is condition number 4 because this is finite. If this is finite, then this is continuous. So for this to be finite, always we must remember that Vr must be finite, the potential must be finite. In the case potential is not finite, this quantity is not finite. Nebulized core is not finite. And if nebulized core finite is not finite, nebulized core u is not finite, then this is not continuous. And our condition number 4 goes away. And all these boundary and continuity conditions plays a very significant role in the energy state also. And also remember that applying the boundary condition, we take care of two wave function. When localized corresponding to bound states, that is energy less than 0, for which the normalization integral converges, and the second one like the harmonic waves of constant magnitude at great distances, and normalization integral of a large distance diverges corresponding to scattering state. Scattering states are represented by higher positive energies, and bound states are represented by negative energies. So these boundary conditions are applicable for a bound states as well as scattering states. So with more applications of Schrödinger equation, we can understand all these things. And also in either case, the wave functions are bounded at great distances in all directions. That means the wave function will be vanishing at the boundaries where the potential will be infinite. And this is what is spoken here. Vx tends to infinity as x tends to infinity. And then definitely there is an infinite number of discrete energy levels. On the other hand, if Vx is a finite value for x tends to plus minus infinity, then there may be both finite or infinite number of discrete energy levels depending on the form of Vx and the mass of the particle. And in this case, if the energy cannot exceed the smaller value between this and this, and that means that energy will be within the value of potential at x equal to plus infinity and minus infinity, and thus leading to a bounded motion for the system. But if the energy eigenvalues exceed the smaller of these values, then they will form a continuous spectrum ranging up to infinity. So depending on the potential, whether it is infinity or finite, we will have infinite number of discrete energy levels, and for a constant value of it, we will have both finite and infinite number in discrete energy levels. And for a case that energy is within the value of potential at infinity and in plus infinity and minus infinity, we have a bounded motion. And for energy eigenvalues exceeding the smaller value, we will have a continuous spectrum. So thus we are left with some assessment here. What is the significance of equation of continuity quantum mechanics? It's nothing, it defines as J and as well as the different conditions of good behavior of wave functions. Also establish the equation of continuity. This is well done here. Discuss what about normalization mean. What does actually normalization mean? As is pointed earlier, it represents the finiteness of the probability. Probability is finite or the maximum probability is 1. Discuss how well-behaved functions is achieved. Well-behaved functions, conditions on the well-behaved wave functions. There are 5 conditions that wave functions must show to prove that they are well-behaved. And only with well-behaved wave function we can find a solution of Schrödinger equations, which will be very clear in case of later course of time. So with this, I'm ending up this video. Hope that this video will be useful for you. You can find the slides here in the comment section of this video. Thank you very much for watching. Bye.